So we can start. So, okay. So in the previous lecture, we introduced the idea of pseudo-random number generators. So if you have any question, I'm going to do like a brief overview of the last lecture so that we can start for the new one. So the idea was we had these generators of this weird-looking sequence of numbers. So we had these weird numbers. And we wanted to understand if there was any pattern, how close they were to random. And we saw that they had nothing to do with randomness because they were generated through completely deterministic rules. They were algorithms, they were procedures that enable us to generate these numbers. And the idea was always, you start with a seed, which is a number, and from that seed, you keep generating other numbers. We analyzed two different generators, one simple one, which is the middle square method, and a more mathematical one, which is the linear congruential generator. So the middle square method works by squaring the seed and taking the n middle digits, and so this is like an example. You have the seed, which is your starting number, you square it, you take the n middle digits, and you have the output of the generator, and the output becomes the new seed. So this is just a procedure to generate sequences of numbers. It is not that good, but it is just a starting point to get the idea. Then we saw the linear congruential generator. This one works with modular arithmetic. So you start with a seed, which is always your first number. And then to generate the nth number, you use the previous one, the x n minus 1. You multiply it with a constant a, you add it to another constant b, and you reduce everything modulo c. And this is an example. Suppose that you have these numbers. The next number is going to be this big 7, 8, 6, 2, 8, 7, 3, 4. So this is the idea. Then we showed how to attack these generators. And to attack it means going from a sequence of observed outputs to extracting the internal parameters. And once you have the internal parameters, you can predict the next number. So you break the randomness because you understand the deterministic rule and you get all the subsequent numbers. And this is bad in terms of security because if you want to, for example, use the next number as a key, now an attacker, I could observe the previous, extract the parameters, and get the next key, for example. So this was just the code to do this attack, which is the slides of the previous lecture are available online. And now we will keep exploring these things about PRNG, and we will see another PRNG. This time it's a bit more complex, but we'll see. But first, I actually want to tell you about a technique for learning actually everything, which is called the black box technique. And I'm gonna tell you this because we will use it in this lecture to learn more about this second PRNG, which is more complex. So, I mean, you all know that computer science, engineering, computer engineering, whatever you want to call it, is a complex subject. Applied cryptography, which is the subject of this course, is very, very complex because we have to do with notions of security, of cryptography, and also about implementations of network protocols. So the question is, how do you deal with such complexity? How do you make sense of such complexity? Now, an helpful idea is to being able to think in terms of black boxes. And I'm going to tell you this, but you probably already did this unconsciously, maybe, I don't know, implicitly. And so you could say, okay, but what is a black box? So when we talk about black box, we have to imagine anything that takes an input and produces an output. So it can literally be anything. Now, what's the helpful idea here? Is that if we think in terms of black boxes, of things that just take an input and produce an output, we can completely ignore all that goes on inside that black box. We just don't care about that. In particular, we can ignore implementation details. So we're just interested in the mapping input-output, what goes in and what goes out. And this, of course, is helpful because it removes a lot of complexity. So when you first approach a system, instead of trying to understand all the details, you should start, I think, by understanding how inputs are mapped to outputs and what are, for example, the characteristics of the inputs and the characteristics of the outputs. And this can give you an overall idea. So this is an example, for example. So now, consider the following code. So this is a C function. It's called fun. We don't know what it does. But we can, when we look at this code, we can do two things. We can maybe at first try to understand all the details, which is hard because like there are a lot of instructions and it is not clear what the function does. We don't have many information. Or we could look at it in terms of black box, which means that, okay, we see that it takes two parameters, which is an array of integers, which is this one. This is the first parameter. And then this is the second integer, which is an n. And like this, intuitively, we might think, okay, maybe n is the size of that array. We can start to make hypotheses only based on the interface, only based on the inputs of the function. And then it does some instruction. We see that it changes the value of this array somewhat, somehow. We don't know exactly how this mapping goes. So we have this picture. We have a black box, takes two things in input and produces, here it says return 0. So it produces an integer. But actually, since this is a C code, what we have is that we are modifying the array that we get as an input. So after the execution, the array will be different. And one can ask, okay, but how different? So we can analyze it when we black box it, we're only interested in what goes in, what goes out, and side effects that could happen. For example, here we have the instruction that modifies the input array. So we modify that location of memory. And then if we white box it, we're also interested about how it works, the implementation details. But as I said, at the first, black boxing is really, really important. So we can test the code. We can just execute the function with a test array. And so this is like an example code. You can find all these code snippets on the material. And this is the name of the file. Now, if we execute it, we see this. So we see that first, this is like before the function call. This is the array. And after the function call, this is the new array. So any guesses as to what this function does? Yes, so this function actually just sorts an array. And we don't need to understand how it works. We just need to see how input is mapped to output. This is called shell sort. It is an interesting sorting technique. It's like n squared, so it's not that efficient, but it's weird. And it was like just to see that sometimes we can ignore the things we don't understand and focus on the little bits just to get an overall idea. And then you can go to the more complex things. So this is a more general topic of interfaces and implementations, which means that when we analyze real software implementations or real network protocols, there are a lot of details, and thus it is actually impossible to understand all the details immediately. So this means that thinking in terms of black boxes becomes a necessity. And this is why you probably already did it, because maybe you faced a project which was really complex, and you started with little bits that you understood, and then you went on from that. Of course, but it is important to remember that this kind of thing is an abstraction. I mean, when you ignore implementation detail, you don't have the real picture, just a model of the situation. So this means that one must still be extremely aware of what exactly is that we are ignoring and what we are focusing on. So if we focus on the interface, we know that we do not know what goes on inside. So we might have the wrong actual idea with respect to the actual software that is running. So this is a general idea to keep a boundary between, okay, what we know as interface, like how input is mapped to output, and what we can also implement, what we know how it works internally, the single instructions and how they make the input go to the actual output. And also I suggest to try and implement a few things yourself, because it is important to have implementation knowledge. And actually one of the hardest things when you implement software, when you design network protocols, when you start to actually not only analyze, but also write this kind of stuff, is actually design good interfaces, meaning good entry points for whatever is it that you are designing, and good output points, so that it is more extendable, maintainable, and things of the sort. So this is, for example, the implementation is the code with all the details, but the interface is simply I have an array, I give it to the function, and I have a sorted array at the end. So this is the idea, and also these kind of things, and if you confuse the two, if you think that you know how the implementation, but you only know the interface, this could be really problematic. And for example, when doing web development, it is actually impossible to understand all the details. So one must be really aware that the code we are writing we don't really know what it's doing. We just have sort of an idea of that. And so this kind of dualism interface implementation applies to all sorts of technologies, even for cars, for example, basically, because one thing is to drive a car to understand how it's driving. One thing is to build a car to understand how it is built. It is intrinsic to technology because every tool is made in one way and is used in a different way. So this also goes for software. The way we use software is not the way it is built, it is different. And I like more implementation knowledge, but this is like my thing, so it's not that important. So now we can actually go on with the actual, with the next PRNG, which is the Mersenne Twister. And all this thing about black boxes will be really crucial because there will be a lot of details here. I will skip some details. I will give you an interface overview of this generator. And then maybe you can, if you want, on your time, understand the actual details. So let's analyze this other PRNG, which is called the Mersenne Twister. It was introduced in 1997 by researcher Matsumoto and Nishimura. Here I put the link to the article. Sometimes when you have the time, it is always cool to actually read the original articles, the original papers. So it is interesting. So now there are different implementations of this generator. This generator has a lot of parameters. We will focus on a specific implementation, which is called the M3-19937, 19,937, I think, which is a standard implementation, which is currently offered by various popular programming languages. For example, Python, PHP, Lisp, which is cool. So, for example, in Python, how do we use this Mersenne Twister? Well, we just import the random module, and the way it works as always. As with any PRNG, we have the seed phase, the initialization phase, and then the actual usage of the generator. So in terms of the way that we initialize, so here we create the random instance, random.random. Then we seed it. We seed it with, once again, a single number, 13337. And after that, there are various ways we can use the random. Here I showed just two calls, which is the method getRandBits and the method randInt. So the method getRandBits gives you the amount of bits you specified. For example, I did the 32 here. So it gets me a number composed of 32 pseudo-random bits. So bits generated through this generator. And then I just print it in this example. The other method, randInt, which is the one below, gives you a number within that range, within the left and the right bound of that range. So for example, the left bound is 10, the right bound is 20. So this might give me like, I don't know, 15, 14, whatever number is between those. I'm not sure if like the edges are comprehended in the interval, but you can look at the documentation. So we can execute the code. We can just call our Python interpreter in that with that script. We get these numbers are big and these numbers are small because the second numbers are between like 10 and 20. So they have to be between 10 and 20. These other numbers, they just have 32 bits. So it could be any kind of expression made up of 32 bits. So the only important thing is that this is 32-bit. So it means that we can go like from 0 up to 2 to the 32 minus 1. So this is a lot of range. Of course, you could say 64, 128. We can ask for an arbitrary number of bits, yes. And we have our number. So this is just the way, I mean, I think that you probably use it if you use Python one time or another, this kind of thing. So remember, so now we will try to understand briefly how this works. So remember some key concepts in the context of pseudo-random number generators. The concept of state is the amount of memory used internally by the PRNG, the memory that is then used to produce these numbers. And then the concept of period, which is, okay, but after how many numbers I get a reset and I start to generate the same sequence of numbers. For example, we could do 1, then 100, then 23, then 4, then maybe I get back to the first one. And since they are deterministic, once you get back to 1, you start the same chain again, because there's no random in here. Everything is deterministic. So once you start to repeat one time, you repeat the entire sequence again. So the concept of period is really important because, for example, in the context of security, we would have generators with large periods. Otherwise, it would be easy to brute force. So what about for the Mersenne Twister in this specific case? Now, the Mersenne Twister is complex because it has a huge state. The state, in the previous ones, in the ones we saw in the previous lecture, the LCG, the linear congruential generator, and the middle square method, the state was always a single number. Now we have 624 numbers, integers, each of which is made up of 32 bits. So this is the so-called state values, which is a term we'll review. And then there is an internal counter, which is other 32 bits. So in total, we have like 2000 bits of state. And here is important to understand this concept of state value. Now, a state value is a single 32-bit integer taken from the 624 that make up the total state. So it's like we can imagine the state as being like this. So we have, here it is an index. It is like a position, a counter, which actually just goes from 0 to 624, but you can store this with 32-bit. We don't care, like we can do that. But after that, we have these state values, which are, as I said, 624. So we have S0, S1, S623, each of which is 32-bit. So like a state value is a single integer. It's like S0, which is a single, or S1. The total state values are the most important thing about the state of the PRNG. So if you have any question, you can interrupt me. So now the thing is, this is cool because this generator has this kind of period. It is 2 to the 19937 minus 1, which is chosen to be a Mersenne prime, and this is called. This is why this generator is called a Mersenne Twister. I mean, we don't really care about this kind of thing, but it's just to understand how the name was gotten. And like a Mersenne prime is a prime of the form 2 to the p minus 1, but p has to be also prime. So if p is prime and 2 to the p minus 1 is prime, we call this thing a Mersenne prime. And Mersenne primes are like interesting for other purposes. For example, there are algorithms that are very efficient to search for really big primes of this form, but we don't really care. I mean, I'm not sure the mathematical detail of why this was chosen, but this is how it works. Once again, interface level, maybe we don't need to know why this is the case, but we need to know that this is the case. So now one can answer, okay, how big is this? So, I mean, when you ask how big is something, what is helpful is to compare to other things, because otherwise it is, I mean, this is just a bunch of symbols. It is hard to understand how actually big. Now, I search online, and it is estimated, at least right now, not sure what will be in the future, but right now, if you count the atoms in the observable universe, this number is between 10 to the 79 and 10 to the 82. Okay. Now, this number that I gave you previously is 2 to the something. So now we have to translate 10 to the something to 2 to the something, and then we can compare those two, like, because if I give you like 2 to the 30 and 2 to the 40, you immediately know which one is bigger because they have the same base. So now we do the following with this, with the total number of atoms in the observable universe, and we can use this function, which is really common and is useful. I mean, the fact that 2 to the 10 is roughly 10 to the 3. So with this, what we have is that the total number of atoms is around 2 to the 280. And now you can compare 2 to the 280 with 2 to this thing. And it's like the difference is really big. I mean, it's like, I'm not sure how good is it to say, but we will probably all die before we see a repetition of this kind of generator. So it's really like if you expect for a repetition, you should not do that. And this is why, I mean, understanding some mathematics is useful to not waste time. So really big. Now, the internal functioning is determined by a series of parameters because, as I said, we have the concept of the Mersenne Twister, which is a mathematical general construction, and then we have our specific implementation, which is that MT19, that was called like MT something like MT 19937, something like that. So this is the specific implementation, and out of this implementation come all these different parameters. Now, once again, we don't care about this. Like, we don't care why these numbers are like this, and it's just a start. We will see a lot of formulas. We don't care. The most important thing is to just ignore the implementation details at first, and also to breathe regularly, because it is important when doing mathematics especially. So like, I'm not showing all the details. I'm giving you an interface level knowledge, and then if you want, you can go deeper and understand better. But it's still important, this interface level knowledge, because it is the starting point, and then you can explore that later. So let's black box the Mersenne Twister. Now, as with any generators, we can model it in three different things. First, it is an initialization step. So it is the way the generator is initialized. Then we have a so-called state update step, and it is when the generator goes from one state to the next. And then we have an output generation step, and it is when the generator spits out a number, it produces an output. Of course, these are linked. In the previous examples, in the linear congruential generator and the middle square method, we did not do this division because they were simple. But now we have to do this division because things get way more complex. So, initialization step. So at first, each state values, the so-called state values, the 624 integers that make up the total state, are initialized starting always from a seed value. So this is a number. So this is a 32-bit number, generally. And out of this number, I initialize the value of all these other things. Now, the initialization is done in a cascading manner, meaning that the state value S of I is computed using the previous value of S of I minus 1, while the first one, which is S of 0, is set equal to the seed value. So we start with the seed value, and then we go to S1, S2, S3, S4, until S623, yes. So like this is the way it proceeds. Again, I'm not showing the formula of how this works, because there's some shift, some store, but just remember this thing. Then later I will briefly show the formula, but that's not the important thing. The important thing is to understand the dynamics of the initialization. So assume there exists an initialization formula which takes an input seed value and produces a full Mersenne Twister state. Now, the full Mersenne Twister state is made up of the state values and also the index. So here I show you how the state values are actually made up, how they work. And so the total state is this. So we have the initialization function, this initMt, takes in input a seed and produces this state, which is like a tuple made up of two things, the index position, which is set to this particular value, 624 at the start, and then each single state values. And as we said, this thing, S0, is equal to the seed, okay? S1 is computed starting from S0, S2 starting from S1, and like that. So this is the way it proceeds. So we have this first building block, the initialization. Takes an input, a seed, and produces a full state, ready to be used. Now, then there is the state update step. So after the initialization has been done, the next time I call for a new integer, the next time I want a new number from the generator, each state value is updated. What do I mean? I mean that, okay, remember that the Mersenne Twister is made up of 624 state values. This means that during this state update step, I'm updating all of them to new values, all of them at the same time. So in general, the state update step happens every time the index position reaches the value of 624. So this index is keeping track of when I need to update the entire state. And since the initialization sets it up to this value, 624, the next time it immediately resets. This is, I don't know why they do that, but it happens. So this is like a dynamic internal. So the new values are updated. At the end of this update, the index is reset to 0 to start the generation of the outputs, as we will see. So we have the update empty function. So we have the init empty function to initialize, and then the update empty function to update. We have two states, the sold and the snew. Sold is the previous total state, and snew is the new total state, where sold was the one that we got before. Like here, I use the k and not S0, because k is simply the number of times I have resetted in a way, like, because the way we have to think about set values is that each time I update, I go from S0 to the next. Since the first state is made up of S0, S1 up to S623, the next available is going to be 624. The next for S1 is going to be 625. So they are different integers. And so I go through each of them. So what it means is that suppose that I start from a general SK after k state values have been generated by the generator. Here I have a state made up of 624, which go from k to k plus 623. So total are 624. Here I have my index position. And then when I do this update, what do? I reset the index position, and then I go and I update each of them to new numbers. So S of k becomes S of k plus 624. S of k plus 1 becomes S of k plus 625. They are just all 624 different numbers. So the new state values. Once again, not showing the details about this update empty function works, but it exists. So also really important, this will be useful later on. To compute the new state value S of k plus 624, we don't need to use all the previous states, but only 3 of them, which is S of k plus 1, and S of k of plus 397. So what this means is that to compute this thing, the new state values, we're going to have a bunch of constants, but we will use this one, S of k plus 1, and then also something that is here, which is S of k plus 397, that particular thing. So we use 3 previous set values to compute the new one. Of course, we combine them, we use other constants, but in the function, they are, this is how they are related. And of course, this also works for this one. For this one, we will use sk plus 1, sk plus 2, and then the other. So each one is made up of 3 previously, combined in particular ways. And finally, we have the output. So we have initialization, state update, and the output generation step. Now, suppose that you have this following internal state. So you have a bunch of state values and a specific position at the value index, which this index is a number between 0 and 624. We could say actually 3, because if it's 4, then we go to the set update. But we can say like 623. So we have this internal state. What is the next number that will be computed when I ask to the Mersenne, give me the next number? So the next number is computed starting from only a single state value. And this is really important. It means that out of all these 624, the next output I see is going to be only a function of one of them. So only one of them will help me to produce the output. And this is crucial. And how do I choose which one? Using the index. So we have that, suppose this is the state, the output of this state is a function of the state value, which is indexed by this thing. So if the index, say, it's like k plus 1, the output observed is going to be a function of S of k plus 1. So only a single state value helps to produce the output. I mean, if suppose that we have like the state S0, S1, and S623, and the index value is 50. So this is like a hypothetical state. If I ask the output with this state, I'm going to get a function of S of 50. So remember, S of 50 is a number. I'm computing a function on this number, and this is the output. Once again, not showing you the details, but we have 3 functions so far. After the state value has been used to produce the output, of course, the index is incremented because it has to say, okay, I've used this index. I need to use the next one. So the state goes from this thing. So here the state values do not change. The only thing that changes is the index. It gets incremented by 1. So this is the output generation. In the state update, all the state values change. In the output generation, they never change, only the index. So this means, really, really important, that each output that I see outside is computed starting from a single state value. So S index gives me output 1. Then I increment the index. The next time is going to be S of index plus 1. Of course, this mapping is not through a function. It's not directly. I don't see directly the state value. I see a function of the state value. But still, it is a function of only that state value. And this is going to be really important because if we see an output and we see that we are using a Mersenne Twister, we will know that that output was computed starting from a function of an internal state of the generator. So after each state value has been used, I mean, when the index reaches this point, 624, the state update step that I described previously takes place. And so all the state values are updated to the next ones with the update MT formula, a different function. So overview so far, we introduced 3 functions. So we have state, which is made up of 624 integers and a position value. The seed is used to initialize the array. The state values are used to produce the output. And after all the state values are used, they are updated at the same time. And this gives us 3 main functions: the init empty, the update empty, and the output empty. Initialization, update, and output generation. Now, out of this complexity, I mean, we don't care about statistical analysis or mathematical analysis. We care about breaking these kind of things. We care about attacking them. So once again, the idea of black box, we just need to know enough to actually predict the next value. That's it. We are only interested in that. So if this is our goal, we can analyze all this complexity. We can reduce this down to 2 things, which is the first one is that the input value generated from the PRNG, the output value here, this is wrong. It should be like the output. The output value generated from the PRNG is a function of only a single state value. So this is key. And then the other thing that is really important is that the update of each single state values, the update of the entire state, is a function of 3 previous state values. So to update S of I to the next, which is S of I plus 624, I actually use these 3 to get the first state value of the next total state. And this is really important. Now, we are now ready to attack this thing. Why? Because, as I said, our notion of attacking is given a sequence of outputs. Okay, here is it. Given a sequence of outputs, we want to predict the next number. Yes?
So the outputs are just sequences of 32 bits.
Yeah, yes. Okay. Yes.
The output is 32 bits.
Yes.
And we have only one seed of 32 bits.
We can assume to have arbitrary many for this time. We can assume to have n. But we will see that we have a specific bound on the number of outputs we have to see before we actually break it. Yeah, no, the outputs, yes, it is a single 32-bit value, exactly, which is computed starting from another 32-bit integer.
A seed of 32 bits, so we have only 32 possible sequences. Right? Each one of these sequences is paradoxical.
Yeah, I think that, okay, so what you asked was, since each output is 32 bits, the space bound for like the numbers that I can expect to see is 2 to the 32 minus 1.
The seed is 32 bits.
Yes.
And given the seed, I can produce those.
Yes.
So it means that I only have 2 to 32 possible.
Okay, actually, this is a good question. Maybe the seed is not bound to be 32-bit. I'm not sure. This is a good question. I should look that up. Because what he asked was, if I have a bound on the seed, okay, like say the seed is like 2-bit, and the seed enables me to understand the entire sequence. I can just brute force the seed to get the sequence I want, and the number of sequences is limited, is bounded by the size of the seed in a way. So this is interesting. Maybe the seed is not bounded, so maybe there's no bound. I'm not sure. I have to look that up, but this is a good question. So the thing is, so suppose now that the seed can be arbitrarily long in a way. So out of these complexities things, because for example in Python actually you can have yeah, I think if I remember well, in the Python implementation, the seed is actually not like there is if the seed is larger than 32-bit, because you can also have in the Python ecosystem, it goes through a weird loop that the actual seed that is used is a different value. It is still 32-bit, but it is computed by like mixing and matching like constant and numbers. So it is not directly seeded as you put it. So this is interesting. So now we can try to attack this thing. So suppose that we have a sequence of outputs. Our problem is, okay, how can I predict the next number? I only see the outputs. I am an external attacker. On the server, there is a generator like this, like a Mersenne Twister, which gives me these outputs, and I want to be able to predict the next one. Okay, so what do? The basic idea is to invert the function that produces the output. Now remember, the function f was used starting from a single state value to produce the observed output. This means that if I invert it, if I invert f, what I can do? I can go from the observed output, which I see, which is the input that I have, to extract one state value from the PRNG, from the state. So this is the idea, invert this function. We will see if this is possible, of course. Now let x of I be the output associated with the state value s of I. So this is like at some point in our state. Okay. So suppose that I have like the state was like I, then s of something, blah, blah, blah. This means that at this point I use s of I to extract, to generate the output. Now I see only the output, but if I invert the function, I can do this. Now, how do we invert this function? Well, we just create a system of equations. Here I showed it. It's not really important to understand the specific, like why they are like this. But the general idea is that I can create a system of equations in which I put, of the variables I put, there's also the state of the single state value that produces that output. So in this system of equations, we have as variables s of I, y1, y2, y3, and x of I. Now, x of I is the output I see. All the others I don't know. But we have fundamentally a system of 4 equations with 4 unknowns, and this system can be solved because you can set like all the things with respect to the various bit representation. And out of this, there are also automatic solver. And in the code that we show later, I use a library which automatically solves this system. So you just put the equations, you say solve, and it gives you all the variables. And of course, out of this, we just care about the S of I. We don't care about y1, y2, y3. We only care about this thing. So this is the idea. Just solve a system. As I said, this is not important, the specific equations. It's just that we set a system of equations. But remember this, like, okay, say that I have S of I extract one state value. But the thing is that the Mersenne Twister has 624 state values. So if I only see a single output, I'm able to construct 1/624 of the total state, only that portion. And this gives a bound on the outputs that I need to see to reconstruct the full internal state. Because if I want to construct the full internal state, I need to observe 624 consecutive outputs, okay, like x of 0, which gives me s of 0, x of 1, which gives me s of 1. up to x of 623, which gives me s of 623. Now, once I have this, I know that after the generator has done this, I have all the state values. The index, I can just I can put it so that I compute the new state values. So the index, I can put it to 624 so that it resets, so that it computes the subsequent state values. And so from this knowledge, from the knowledge of S0, S1, S623, I can know everything fundamentally about this. Now, recovering the state. So as I said, to recover the state, we need to observe 624 different outputs. From each of those, I construct each single state value, and this gives me the entire state. Once we have recovered the full state, we can synchronize a local implementation of the Mersenne Twister with the remote one we're trying to attack, because we have synchronized our states. So in the case of LCG, if we remember, in the case of LCG, to synchronize the state was to understand these parameters, these LCG parameters, which were 3. Now, to synchronize the state, we need 624 parameters. But once we do that, the same idea applies. I can predict future values. So the idea is, when we want to attack a Mersenne Twister, what we do is we observe 624 consecutive outputs, and they have to be, so here are a bunch of things to mention. They have to be consecutive, and they have to be the direct output of the PRNG. I mean, I have to see actually what the PRNG produces. Because here, two things could go wrong. Maybe I don't see direct outputs, consecutive outputs. Maybe I see x of 0 and then x of 3. Now, the attack I'm describing does not work with this. There are other attacks. It takes longer, it takes more values. Another thing could be that I don't see the full output. Okay, I don't see x of k. I don't see the output, but I see a function of the outputs. I see a function. Maybe I see only the last 2 bits or things like that. So the output is masked with something else. In those cases, if I can revert that something else, I can back the original output and I can still do the attack. But it adds a layer of complexity that we are not assuming here. Here we're assuming basic things. So I observe the outputs, I reconstruct the internal state, and then I can predict the next outputs. So this is like observe, reconstruct, and you can predict the future. Because once I have the full state, I can synchronize and then I can go forward. But there is another thing, is that after we have recovered the full initial internal state, we cannot only go forward. We can also go backwards, because we can invert also the state update function. And this means that we can recover the entire history of the numbers generated by that execution of the PRNG. And why we can do that? Because we can also invert the state update function. So, I mean, this is a common theme in cryptography. If you want to secure things, you compute a function of those things. So you go from something to something else, right? You go from x to f of x. In terms of breaking things, it is always the inverse. We have to go backwards. And if we can do that, then we break. If we cannot, then we don't. But this is the general idea. In this case, we have 2 main functions, the output generation and the state update. They can both be invertible, so they are not really secure. So yes, this was just starting from S of I. We can essentially, you can set a big equation that sets the state that we have with the previous state, and we can recover the previous state, because we have enough equations, enough bounds on the system. So I mean, no need to build a time machine. We can go backwards just by seeing the outputs. So we can recover the entire history of numbers generated, and this can be critical because it is not only critical to see the future, but see the output is actually even more, because it means that you can attack someone retroactively. It means that a key generated in the past can be recovered, even if it is being deleted, maybe. So, as I said, we can observe the outputs, reconstruct internal state, predict, and then compute past. Predict next and compute past. So, I mean, is this all? Of course not. I mean, I left out some mathematical formulas and code. How is this actually implemented in Python? I mean, for performance reasons, it is implemented as a C module. So it is C code, it's not Python code. And its implementation can be found in this file. in the directory modules, here I put the link to the CPython project on GitHub. It is interesting to see the actual code. I mean, I'm not going to show it. But for example, just to give an idea, we're not going into details about these formulas, but to give you an idea about the initialization. So we set the S0 to the seed, and then the SI is computed with this formula. So we have this constant times this value plus I, where I is the index. This other value is the previous state values. As I said, the previous state values is used to compute the new one. The previous state values, which is XORed with the previous state values shifted to the right by 30 bits. So this is the formula. You can actually implement it in the C code. This is implemented in C. And this is the state update. So what do? The thing to note here is that to compute the S of k plus 624, we use only 3 previous state values. S of k plus 397, S of k, and S of k plus 1. All the rest is just constant, is just masking bits with AND, with OR. And then there is this function, this A function. I mean, as I said, no need to go into the details, but this is just an idea of how this is implemented, which takes an input, a mask of bits, and it gives the bits shifted by 1 to the right, or the bits shifted by 1 to the right and XORed with a constant, depending on the lowest bit of the input. So if the lowest bit is 0, you do just a shift. If this 1, you do the shift and XOR. So this is how it is implemented in the C. And finally, this is the output generation. Here I show the code and not the formula, because I think it is clearer like this. So we have, I mean, this is the object which contains the state of the Mersenne Twister. This Y represents the, for example, S of I, because empty is the array of state values, and we access empty using the self index, which is the position. And then we do the post operand so that we access the element and then we increment the index later. After we have the S of I, so now we have the S of I, then I do this. I do S of I, XOR, S of I shifted to the right by 11, and then this other thing, and then this other thing, and then this other thing, and then I return it. So I do some XORing, shifting, masking with constants, things like that. Not important the details. That's how it is implemented. If you want to actually understand the details, I can give you some more resources to actually even understand implementation, because the implementation, like the way it is implemented, things like that. So now let's see an actual attack, meaning like a scenario in which something like this could be exploited. But before doing this, we can do like 5 minutes of break. We can do 5 questions.
I think that the main problem
yes.
of this pseudo-random generator is that we use F, which is reverse support.
Yes.
But what about if we use a function that can be reversed?
Yeah, I think that we will see at the end other kinds of generators, and those other kinds of generators, they do 2 things. One is, as the colleague said, they use, I think, I'm not sure, I'm not 100% sure, but I think that they combine 2 things. They use functions which are hard to revert, and also entropy sources. We will mention something about entropy at the end, but they combine those 2 things so that you have an invertible functions, and you have an hard time to like, and it is always different, something like that. But now we do the like 3-5 minutes break, and then we keep going. Okay, so we're gonna start. Please, attention. Okay, so I mean, so far we gave a general idea about this Mersenne Twister and the weak points, which, as I said, is the invertibility of these 2 functions, which is the thing here. So this thing. So since we could invert the output generation function, the state update function, we can attack it. This is the weak point that we're going to exploit. So how I showed how to exploit? Well, the idea is to I've written a web app that uses this kind of generator, and we will attack it in actual practice. So you can download the resource code at the following URL. It is a zip. You open it, and it has a bunch of files. There is also a directory which is called example3 web app. Now this directory has itself a bunch of files, and they are all Python files, some TXT files, some HTML files. It is a web application. Now these files and directories implement a web application written using Flask, which is a Python library. Now you don't need to understand the details of Flask. I will show you how to run it in a black box way. Just execute the code and you get it up. So how do we execute it? So to execute the application, you need to, of course, satisfy the dependencies and start the web application. So to satisfy the dependencies, I suggest to create a virtual environment. Now, this is a Python-specific thing, which essentially wraps all the packages that you download with pip. Not sure if you ever use pip, but a virtual Python environment is just so that you don't mess your entire system. You just do this, so that if you broke something, you eliminate the files and nothing changes elsewhere. So this can be done with the following commands. You have Python, you have the interpreter, you do Python 3, this thing, vm, which is the command to create a new virtual environment, and then you give the name of the virtual environment, and then you have to activate it. And to activate it, you can do within a shell, you can do the source command. So source, starting from the folder where you created, you execute this script. So what does this do in terms of the environment of execution? It makes sure that when you download packages, they are downloaded in this particular directory, new environment. And then to install the dependencies, you can use pip. And in the folder, there is a file called requirements, which has all the dependencies. So you can do just to pip install r and then the requirements file. I mean, for example, just to show you, if you never use it, I mean, the first times can be a bit, just remember the commands. So we have, here we have a bunch of files, okay? I have my Python interpreter. This is Python. I do Python 3, the env. This is the command to create an environment, and then I have to say the name, new env. So this creates a new environment. So now if I do ls, I will not have a new directory, this new env. If I go inside, I have a bunch of files because this is a Python environment, but I don't care about those. I do source, new env, bin activate. Okay. Now here the prompt changes. I have this new env because now if I do pip install a new package, it's not going to be installed on the entire system, but in this directory, which means that when I'm bored and I want to delete everything, I remove the directory and nothing breaks. Then we go inside the example3 directory. I have this requirements file, okay, this thing. If I check the contents, they're just a bunch of packages because web development is hard, so you have to install a lot of dependencies. We don't know what each of them do. I mean, black boxing, so who cares? We do pip3 install r requirements. So this is the command to install the list of requirements. Now they're going to be installed, and so this is the way to set up the environment. It's just a bunch of commands, and we are running. So now we can start the application. So to execute the application, you do Flask run within the folder of the application. So in that example3, we have this file up. Now, if you do Flask run, it says this is a development server running on, and then it gives you an HTTP endpoint. So to connect to the application, you use a browser, okay, like this. Wait, this. Oh, cavolo, è vero, aspetta che cambio il tema. I will change the theme. Thank you. Okay. So, fuck that. Oh. Okay. Sì. Okay, so we have our environment. So for those, if it was not like It's not that clear to create the environment. So once again, fast run, you do Python 3, env, m, new env. Okay. So then you do source, new env bin activate, and then you go inside the, so here I have the lectures, the code folder. Actually, no, this was the problem. You do here, and then you go example 3. We have a bunch of files. You do pip3 install our requirements. So you install all the requirements. Okay, and then you do flask run. Then it says this is a development server, and it gives you an endpoint. You take this, you go to the browser, you go to this endpoint, and you see a login page. Okay, now what you can do in this application is you can try to log in. There are 2 users, admin and Leo. You can register, and you can request a reset for your password. So pretty basic. So when you register, suppose I register the user Bob, testcrypto is art.com, password, I register the user, and then this app tells me, okay, to reset your password, you have to save the following code. So, I mean, this design is not that good, but whatever. So we have a password reset code, okay, which is a number, okay. So we save this number somewhere in our notes. We say like here, we have this number, this beautiful number. So we can log in. I put Bob and password. And this is, I mean, this is my web app. I'm not a web developer, sorry. So welcome. Now I suppose that I forgot that my password was password. I can reset it. So I request a reset. But here it says, yeah, I gave you a reset code. Now you have to give me the reset code, and you have to put a new password. If I put like a random code, I cannot say it's not good code. If I put the correct reset code here, I put A, which has new password. I changed the password because I don't like when they ask you to put like letters and dots, things like that. So it's pretty clear. So I change the password and I can do this. So now this design is very, 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 very vulnerable. And why is that? So let's go back to the slide. So web app overview, we kind of saw it. So we have login, register, dashboard, the recover password in terms of functionality. Login page. Now we can log in with these credentials, okay, but we don't care because we're gonna break it anyway. If the login is successful, actually the app generates a JSON web token. We don't care about that. It's just a cookie for saying that you actually log in and you can access your pages. The registration is another form, which takes other fields. And then when you register, you get the reset code, and you can use it to reset the password. Cool. Now, we have this number, like when you type with the OTP. Now, the thing is, if we register different users, we get different numbers. And I mean, at this point, when you look at, like, for example, the number generated by the OTP, it's like, okay, but how is it generated? Because if it's generated naively with the methods that we showed, it is easily breakable. So are they random? I mean, at this point, we know that random means nothing, but how much randomness do they have? It's like randomness is more like of a property. You can have a lot or nothing, or in the middle. And the more random you have, the harder it is to predict. So where's the vulnerability? Now, as I said, you don't need to understand the Flask code because it's not the scope of this course to do web development. The important thing to notice is the vulnerability. And if we check the code, how the numbers are generated is that a PRNG, of course, I brought this code to be vulnerable. I mean, I hope, for God's sake, that this is not used in real things, but you never know. So this is clear vulnerability, but maybe something like this could be used. I don't know. I hope not. I hope not. Let's assume not. So the thing is that this is the code of the web app, and it uses a Random.random, which is a Mersenne Twister. And of course, here I generated the first two numbers just to simulate the fact that the first like 2 users registered, maybe something others, something like that. I mean, here we know the seed, but suppose that we just know that it is a random.random. We don't care about that. So when we register, when we do the registration, we check, for example, if the user is in the database, in case we say, look, the username was already taken. Otherwise, we generate another number using the same instance of the generator. This is important. So we have the same instance that is used across all users. And we get this thing. We get the next number, the next 32 bits of the state. And then, I mean, this code, we don't care. We just generate this. Now, why this code is vulnerable? It's vulnerable. I think this is written wrong. Because the thing is that if I register multiple users, I can see multiple consecutive outputs. I mean, assuming that I'm the only one attacking. It's just like a game. It's not really real. Because in a real scenario, there is an added complexity, which is if it is used across all users, then I need to make sure that what I see is consecutive outputs. Because if I do one registration and I get one code, and then in the meantime, another user does another registration, the one I'm going to get after is not the consecutive, but the one, the other two. So I mean, this is the idea, pretty simple. The code you can actually see. I mean, it's not that crucial to understand or to see if you want to play around. It's this one. It's not written that well. I mean, as I said, not web developer. But this is the vulnerability, and the rest is just a structure to make sure to exploit. Now, the good things about this thing is that it also creates an environment in which you are not only doing an exercise with like pen and paper, but you're actually using technology which could potentially be used to attack a web server, of course, for ethical reasons, to protect it. So the attack. So remember what we said about the attack. So the idea is observe the outputs, reconstruct the state, and predict the next, and compute the past. So in particular, what we want to do with this is that we want to reset the code of all the users of any number of users we want that were registered in this site. We want to synchronize with the PRNG running on the server, and we want to predict both the future reset codes and the past. And we want to reset the passwords of all those users. So we are able to observe 654 consecutive outputs by simply, I mean, as I said, this is simple because we are running locally. It's not really. After we observe those, we can simply recover all the reset codes, and we do not have to interact with the server. We just need those outputs. We will know the reset codes for any future users that will register to the system and for any past user. Like, for example, when you use OTP services, one-time password generators, they have to be somewhat deterministic, or they have to like update deterministically. So maybe if you break the OTP of one user, you can have the next ones, and you can hack into the account, maybe. We will also be able to go backwards, as we said. Means that we can reset the password of the admin user, of Leo, and things like that. I mean, technically, speaking about like if we were doing a pen test to this application, the thing is that the application, when you reset the code, it doesn't tell you the username of the user you are doing. So there is another complexity of also discovering the usernames. But I mean, this is just an example, just to play around. So what do we do? I mean, this is the attack. This is all the attack. I mean, of course, it is not all the code, but we call various functions. So what do we do? First, we define an attack range, which means when you synchronize the local state, go back 50 users so that you reset the password of the last 50 users. You could put this to like 1,000, 100,000. It's not that big. Then we put the new password, pound, which is the password that we are resetting to, so that everyone will have the same password. And then here is the actual thing. So first, we collect the outputs. Okay, and this function, of course, has to implement the interaction with the HTTP server, the interaction with the server, and the extraction of the registration code. I mean, as I said, this is out of the scope of this course in particular, so you don't need to worry about the implementation. But the code is there if you want to see. So we collect the outputs. After we have all the outputs, it's going to be a list of numbers. So I'm going to have a big list of numbers, 7474, things like that. After I have this list of numbers, I can use another thing, which is called recover PRNG state. So this function produces the state of the remote Mersenne Twister that I'm trying to attack. And it's going to be another list of numbers. It's going to be the list of the state values, essentially. So I'm going to have state values 0, state values 1, state values 624. Each of these state value was computed using a particular output obtained previously. Once I have this state values array, this list of state values, I can, of course, start to generate the next number. But here comes like an issue, is that the Python interface to access the Mersenne Twister is defined in such a way that I cannot tell it, okay, start with this state, because it is used internally, it is hard to do. So to actually do the attack, I've implemented in Python a custom version of the Mersenne Twister, which is the same as the one implemented in Python. I mean, this is confusing because the one implemented in Python is written in C, and it is executed by the interpreter. I've written in Python, high level, another generator, which implements the same thing. And in my implementation, in my custom implementation, I can say start from this state and go forward. So I have this added ability. And when doing exploitation, this is really common theme. You have to simulate the environment, but also you have to add certain things and things like that. So then what we do? We do this untwist, because when we recover the state, we recover the state after 620, like 4 or 5 requests, because we have done this request to recover the state. So we have to go back. And once we go back, every time, every next step back is going to be actual reset codes valid reset codes, because if we check the timeline of the reset codes, we have like reset code 0, reset code 1, then we have from reset code 2 to reset code 2 plus 620, like 5. These are ours, so we don't care about those. So this thing is just, and then we reset here. Here we do 2 plus 670. Here we synchronize with the local, but now we have to go back. So this is like padding. This is like not really interesting. Those are the interesting one, the one previous of that. So we do the untwist one, and then once again we do the we get we start to generate these random numbers, and when we generated random numbers, we are regenerating the ones that were generated by the application at the start, because it's like we go back L0, L1. Here is all the padding, 600. Here is all the padding. So we go back to the start, and then we keep generating these things, which are the interesting ones. And for each one of those, we try to change the password with the code and with the new password that we put here. So I mean, this is just overview, high level. So to actually work, I've implemented this custom. You can find it in here. I mean, it's not that important, but if you actually look at the code, it implements all the mathematical equations that I showed you at the end. So like these things, they are implemented, of course. So we collect it. So this is an example execution. So we can try to simply execute it. We have the app running. Okay, we have the app running. Because if I go here to here, the app is running. Okay, so we can do Python 3 attack. We can just execute the script. So it's going to collect all the outputs. This is collecting the outputs. Then we're going to recover the state. We're going to recover the 624 state values, which are also integers. So it takes a bit to recover the state. So if you look at this, this S623 is like the the last state value, and then just a list of state values. They are 600. So this is the idea. And then at the end, we can see that the next number is going to be this. Let's try. So it's like 3 something. Let's see if I failed. So register, test, test. So it is 32798555066. So we have predicted the next one. So it is correct. And then we also change the password of the users before. So if you go here, I mean, you don't see the password, so I could lie to you. But if you think about it, the legit password is very long. I'm going to put 1, 2, 3, 4. I'm going to log in. So it's you can try yourself. It works. So this is, I mean, this is just some small example. And I mean, you can do various things. You can play with this app. You can try to implement the Mersenne Twister yourself. There are these challenges, which are called the CryptoPulse challenges. But this is up to you. I mean, it's not really mandatory. It's only if you're interested in these sort of things. So to finish off fast, like 10, 20 minutes at most. So we have seen that random numbers are hard to generate, and now we understand better why this is the case. We broke actually generators of pseudo-randomness. We have described 3 different generators, and we learned how to bypass the randomness. We learned to bypass the rules. So now what do we do? If we want to actually generate safe things, like a safe reset code, I mean, we have safer alternatives. And here comes a new term, which is cryptographically secure pseudo-random numbers, number generator. So cryptographically secure pseudo-random number generator, or cryptographically random, I'm not sure, like there's another way which is shorter. But the general idea is that you take PRNG and you put cryptography in a way before. So this is pretty easy. Now, a secure generator has to satisfy 2 properties, which is called the next bit test and the state compromise extensions test. So this test is like, this is a bit formal. Given the first k bits of a random sequence generated by this generator, there is no algorithm, which is polynomial time, which is fast, which is actually usable, that can predict the next bit with probability of success better than 50%. I mean, this means that if I see a bunch of outputs, which means a bunch of bits, because the number of C are just like a bunch of bits, and I ask, okay, but what is this next bit? The best I can do is guess. I have 50% of correct, 50% of correct. There's nothing that can, no matter how many bits. So given the first k, but k is general, I can see arbitrary many. For example, the Mersenne Twister fails this test because after 624 inputs, which is roughly like 9,000 bit, so there are a lot, but it works. I am able 100% to predict the next value. So no matter how many outputs I see, I'm not going to have a good time predicting the next value, the next generated value. I mean, if I can, I broke cryptography, I become rich, and it's hard. So you shouldn't. I mean, it shouldn't be possible. Of course, these are all research questions, but yeah. Now this other has to do with, now suppose that part or all the state has been revealed up to a certain point. Like at some point, I reveal the entirety of the state. A cryptographically secure generator should not make so that if I reveal the state at the point t, I'm also able to generate the previous values. I'm not able to go back in time. So I'm not able to go from the future state to the past state. The past state should be not accessible anymore. It should be, and formally it should be impossible to reconstruct the stream of random numbers prior to the revelation. And it also says, additionally, if there is entropy input while running, it should be feasible to use knowledge of the input state to predict the future conditions. What does it say is that, now here it mentions this concept of entropy input. Now, I did not have the time to talk about entropy. I'm not sure if Professor Bianchi told you something about it, but entropy fundamentally is like a practical source of randomness. And most of the time, entropy is obtained through physical phenomena. Now, the entropy source, entropy input, is like is like a circuit that connects to my PRNG and gets information from the outside environment. This means that even if I break the state at one point, the next time, the next output generated will take a function, the state, but also the entropy input. And given that entropy is made so that it is hard to, for an attacker to get the same entropy as yourself. Like, for example, if I use like, I don't know, the way that the electricity runs in my laptop when I use it, an attacker, I mean, it is really hard to simulate the hardware scenario at that level of detail. So it's not going to be able to have all the inputs. And so it's not going to be able even to predict the next outputs. But this requires entropy. So this is visualization. I mean, this is to say, this is, but it's important to note that, I mean, there are various ways. But before showing the various ways, like, for example, I can show that. For example, in Linux, you can use the device driver dev.random like this. So you do head, which takes the first 500 bytes from this. Now, device drivers in Linux are like files. You can access them like files. With this command, you are creating in test.txt 500. You are putting in that file 500 random bytes, which are constructed through cryptographically secure generators using also sources of entropy. And then, like, you can get the size. The size is perfectly 500. You can change, of course, this number to whatever you want. If you do an XDump, you see a random bunch of random bytes. So these are the actual bytes, okay, the values. It is not, of course, text. You cannot read it because it is random data. So if you need something, you can maybe do a call to dev.random. But if you use Python, it is much simpler because it implements an interface, which is called os.urandom. So it is not import random, actually. It is import os and os.random. So this function, this small function, generates an hexadecimal string. So it is like a digest, like an hash function, which we will see later. So if of the given bit size, so you say, I want 600 bits random, and I give you a string which encodes all those random bits. And here I call it 3 times, one with 8 bits, one with 16, and one with 32. And then this is the output. So this first is with 8. So these are 8 random I'm not sure if they are bits or byte. So this you should check. So not sure that, but yeah, you get this. Now, to finish off, are they always better? It is always better to use a cryptographic alternatives? Of course not, because they are more expensive. I mean, everything that you get, you have to pay in other ways. In this case, entropies are to generate, so they should only be used for security reasons. And this is important because if you start to use them for all kinds of purposes, you reduce the entropy, and then the security applications become weaker. So you have to ask yourself this, so a big picture. And I mean, you know, this thing, this meme is actually profound because to build muscle, you have to put a lot of effort. If you don't have one muscle, you gain in other ways. So you always have to pay somewhat. And the PRNG shouldn't feel bad for not having muscles. It's not to be used in a cryptographic environment. I mean, we always have to understand the correct context in which to use our tools. So they are always better? No, they're not. So a big picture. So in this 2 lecture, we have seen that through generators, we're able to use pseudo-randomness. However, pseudo-randomness is not true randomness. I mean, true randomness is really abstract idea. So before using classical generators, meaning non-cryptographically secure, you should ask yourself, is it a problem if a human mind is able to either guess the next number or the previous one? If it is not a problem, if like no one cares about that, then you should go with the classical generators because they have no security implications and they are more efficient. And they probably have, yeah, they are more efficient, they require less resources, etc. If instead this is a problem, if it is a problem that a human mind could be able to guess the next number, given certain condition, etc., you should use cryptographically secure. Of course, they do not guarantee this because then you have to ask yourself, how are they implemented, if they have bugs, things of the sort. But in general, as an end user and as a user of these things, if you see a protocol, if you see something like that, which requires generators, which requires numbers, and these numbers should not be able to be guessable, then use cryptographically secure. If it is, you go with cryptographically secure. Otherwise, you stick with classical generators. And so this is it. I mean, I have some references, not that much. And this is over. So the lecture is over.